they are the structure-preserving maps of topology. That's exactly. It's a very, very deep question because mathematicians always classify structures by identifying them if certain structure-preserving maps between them exist. Okay, so let's have a question at this point. So let's make an example. No, I already have an example. I would like to write down the mnemonic phrase. So if you want to remember this definition, it's very easy to remember. A map is continuous if and only if, when it's if of a definition, so exactly is continuous, if the pre-images of, what is all of course you mean, open sets are open sets. The pre-images of open sets are open sets. The only point is the pre-image of open sets, and here you should say in the target space, are open sets in the domain, because the pre-image lies in the domain, and the pre-image of a map of a subset needs to be a subset in the target, because otherwise you can't take the pre-image. So the short formula, pre-images of open sets are open sets. These open sets refer to a topology on the target, whereas these, of course, must refer to a topology on the domain, as is written down precisely here. Okay? So that is... Yes? No, and I can't, because I didn't emphasize that the standard topology is only defined on R to the D. This here is not an R to the D, so on this one I can't define the standard topology. It's a very important thing. So, and the standard topology, it has this effective name standard topology, as if there was anything mathematically special about it. There's nothing special about the standard topology, other than that you like it because it was the first topology you implicitly met in the beginning of your studies. Okay? But that's not a good reason for space-time to carry it. Right? So this is a very important point. It's called standard, and that's reconciled, makes you, I mean, this is somehow to make you happy, and other people do the same trick. But it means nothing, and it can only be established on some RD, whereas on an arbitrary set it can't even be talked about. Okay? Very important point. So we take it always very general, unless we say which one we chose. Okay. So, okay, let's make an example. And in fact, I had one. I don't find it, so here it is. Example. So let's say n is the set 1, 2, 3. We had it before. And let's say n, the target, is the same set. Why not? I can go from set 1 to 3 to the set 1 to 3 with a. Let's go make it even simpler. Only set 1 and 2 and 1 and 2. So let's invent a map. One map is, there's the 1, there's the 2, there's the set 1, 2 again, and just for fun, I map the 1 to the 2, and I map the 2 to the 1. Why would I not do that? That's the map F from n to n I want to look at. Okay? Very simple one. And now I establish topologies on these sets. And I choose, that's the definition, I choose to establish on M the topology with the elements empty set, set with element 1, set with element 2, and set 1, 2. This is a topology. And on n, I establish a different topology. Although it's the same set, I'm free to choose a different topology. I establish the empty set 1, 2. That's a topology 2. So the question is F continuous? What do we have to do? To check whether F continuous, again, not all by itself, but with respect to the chosen topologies, whether F is continuous, we need to check what is the pre-image with respect to F of just every open subset, that is all, for all, for just every open subset in the target. We need to check whether the pre-image lies as an open subset in the domain. What are the open subsets of the target? Well, I can completely enumerate that. I need to study these two pre-images, because these are the only open sets in the target. What is the pre-image of the empty set? What are all the elements in here that come to lie nowhere? None. Because it's a map. Everything is mapped by the definition of map. What is the pre-image of the set 1, 2 with respect to F? Well, set 1, 2 is the entire set. The pre-image is the entire set. So this is all of M, correct? But all of M, by the actions of a topology, lies in OM. And the empty set also lies in OM. So in fact, we checked that F is continuous. This map is continuous. Now you will be very surprised, because this was only part A of it. Now I do part B, and I do the following thing. I now look at the map that goes the opposite way, that starts in here and goes in here, which as a set is the same thing, so I call this the map G, because it has a different domain, different target. And again, N is 1, 2, M is 1, 2, and the G map we define by this. You see, it's the same map. Has exactly the same prescription, yes? Okay, so Should we talk about this equal sign as a question, or? Okay, so the point is the pre-image of the empty set with respect to f is, let's see what I was right, is the set of all m in M for which f of m lies in the empty set. Now, if f is a map, then every element of M is mapped to some element of the target. So it's an element of the target, but not of the empty set, because if f of M was in the empty set, then this M wouldn't have an image. But because f is a map, every element here must have an image. If the map would, the notion of a map would allow for this little Christmas tree point here to not be mapped. If this was still a map, if only these guys are mapped, but this one isn't, then the image of this under f would be nothing because there's no image. Okay, no M in M satisfies this. So you take all the M in M that satisfy this condition. But any M in M is mapped to a non-empty, to something in M. Hence, none of these satisfies this condition. So no condition I showed that means it's the empty set. I think it's clear. It's ultimately the definition of map. Maybe we can discuss later if you're satisfied. I think that's true. Okay, so now we go the opposite direction. I again give this prescription, say, oh, it's the map F. Because, well, M actually is N, and, okay, you're right, it's actually the map F, but not if I keep with it that the M is equipped with one topology, and the N is equipped with another topology, because I now have this other topology on the domain and the other topology on the target. I could have also said I swapped the topologies, but you can also think of this G as the inverse of F, the inverse map, because that is what it is, right? It changes one true and it changes it back. If the map is continuous, the bijective map, the inverse will be continuous too. Well, check for every open set in here, check whether the pre-image is open. So we start pre-image with respect to F inverse of 1. So I take an open set in the target. Let's start with this one. Of course I start with this one because it already spells catastrophe, so I don't need to write so much. So it is true, I must check for every open set in here. So for instance for this one, what's the pre-image of the set with the element 1? Well, it's the set with the element 2, right? But the set with the element 2, unfortunately, cannot be found anywhere in the topology of the now domain. Not continuous. This inverse, not continuous. And to make it even worse, if I hadn't exchanged 1 and 2, it would be the identity map. From one space with one topology to another space, to the same space with another topology, the identity map could be continuous in one direction, and the inverse of the identity map, which is of course the identity map again, could be not continuous, because it shows different topologies. Do you see how dangerous it is to not explicitly talk about the topologies?